Thank you very much, Kevin, for such a kind introduction, and thank you very much for having me here and giving me the opportunity to present my work. So the project I'll be talking about is titled Inference on Local Variable Importance Measures for Heterogeneous Treatment Effects. And this is joint work with Alex Ludke and Peter Gilbert, and that's project I was working on mostly during my time at UW as a postdoc. So before I move forward with the topic, let me do a little bit of advertisement. Copenhagen is a very beautiful city, as you can see, and it also has a great biostatistics research group. So if you would be interested in short or long research visit, then please let me know. So here on the bottom right, you can see Nyhavn, which is center of Copenhagen, and bottom left, you can see one of the buildings where biostatistics is located. Okay, but let me move to the main topic of this presentation. So in high-risk domains, for example, in medicine, decision makers may hesitate to rely on the black box decision support systems without understanding the rationale behind the recommendation. So goal of this project is developing an inferential framework to assess variable importance, and especially in the context of heterogeneous treatment effects. The variable importance measures that we consider are local in that they may differ across individuals, while the inference is global in that it tests whether a given variable is important for any individual. So maybe let me just mention briefly for maybe those of you a little bit less familiar with variable importance literature. So when talking about variable importance measures, people commonly distinguish between so-called algorithmic variable importance measures and model agnostic variable importance measures. So in case of algorithmic variable importance measures, you would usually have in mind some algorithm that you want to use, some prediction model, maybe based on neural networks or random forests, and then you would be interested in kind of variable importance from the point of view of this algorithm, like how different features influence the predictions of a given model. Whereas model agnostic variable importance measures tell us something about data generating process. And in this work, we are interested in model agnostic variable importance measures. And furthermore, model agnostic variable importance measures may be distinguished between global variable importance measures and local variable importance measures. So global variable importance measure would be average across the whole population. So for example, if you think about ranking of variable of importance, that would be a single ranking for whole population. Whereas in case of local variable importance measures, different individuals may have different importance of a given feature. And in particular, you may have a different ranking of importance of different variables for different individuals. Okay, so after this brief introduction, let me introduce a problem setting. So let X be vector of covariates sufficient for confounding adjustment of a binary treatment A on outcome Y. The main object of interest that we will be studying is conditional average treatment effect given by formula 1, which is just treatment effect conditional on some subset of covariates. And here YA denotes the potential outcome under treatment A, and S is a subset of indices of covariates. So under causal assumptions, usually invoked in causal inference literature, that is assumptions of positivity, consistency, and conditional exchangeability. This Kate function can be identified by statistical estimand given by the formula 2. So moving forward, this function nu given by formula 2 will be my main object of interest. However, if you are willing to accept these causal assumptions, then it can be interpreted as conditional average treatment effect. Okay, so the question we are interested in this project is how to quantify the variable importance for Kate. So a popular class of variable importance measures are so-called leave-out covariates or local variable importance measures. So leave-out covariates variable importance measure for Kate is given by formula 3 and is defined just as a difference of two Kate functions. On one hand, Kate, where we are conditioning on subset of covariates X plus covariate I, of which importance we're interested in, minus Kate conditional on subset of covariates S alone. So here we have some flexibility in terms of defining the subset of covariates S. So for example, if we set it to full vector of covariates X except of feature I, then this gamma I corresponds to so-called leave one out variable importance measures. And on the other hand, if we set this subset of indices S to empty set, then gamma I is keep one in variable importance measure. Okay, so given that we have defined a candidate variable importance measure, we may be interested in testing null hypothesis of zero importance. So our null hypothesis would be that gamma I is equal to 0 p almost surely against the alternative not H null. So an initial proposal that one could consider would be to define a test statistic being squared L2 norm of gamma I. However, there is a problem here, namely under null, the efficient influence function of this quantity is equal to 0. So this means that we would need higher order parameter expansion to develop valid tests. However, in case of this parameter, like it's not sufficiently smooth to perform this higher order parameter expansion. So as alternative solution, we propose to consider reproducing kernel Hilbert space embedding. Okay, so let me provide a little bit of intuition behind RKHS embedding. So for a symmetric, continuous, positive, semi-definite kernel function K, we can define RKHS embedding through this formula 4. So let's try to understand a little bit better what this mapping does. So here I'm presenting two graphs where red curves correspond to original functions and blue curves correspond to their RKHS embeddings. So on the left-hand side, we can see that our original red curve is already fairly smooth and well-behaved. So RKHS embedding does not change much. However, when we look at the function on right-hand side, it's more wiggly, less well behaved. And now we can see that we get quite a bit of smoothing out through performing of RKHS embedding. And importantly, RKHS embedding is injective for an appropriate choice of the kernel. And so what I mean by appropriate choice of the kernel is if the kernel is universal. Okay, so now we're well positioned to define RKHS embedding of the local variable importance measure, which is given by Formula 5. An important result that we will rely on is that RKHS embedding of Kate function is pathwise differentiable and has efficient influence function. And as immediate result, since our local variable importance measure is just difference of two Kate functions, RKHS embedding of the local variable importance is pathwise differentiable and has efficient influence function. So now, given that we have efficient influence function at hand, we are well positioned to construct one-step estimator of the RKHS embedding of the local variable importance measure, which is given by Formula 6 and has usual form of one-step estimator, that is plug-in estimator part and bias correction term, which is mean of efficient influence functions. Furthermore, for this one-step estimator, we have the following weak convergence result given by the expression 7, where this limiting object, HS, is a Hilbert-valued Gaussian random variable. And given this weak convergence result, we will be able to perform statistical inference and in particular build hypothesis test for our null hypothesis of zero importance. So the equivalent test of zero importance that we propose goes as follows. So the null hypothesis is that the RKHS norm of RKHS embedding of gamma I is equal to 0 against the alternative that it's different than 0. So here one rejects the null hypothesis if the RKHS norm of the one-step estimator is larger than square root of psi hat over n, where here this psi hat is 1 minus alpha quantile of squared RKHS norm of this limit object from our weak convergence result. And importantly, we are able to approximate this quantity using Bootstrap. And importantly, this test asymptotically controls type 1 error at level alpha, and it has asymptotically non-zero power against local alternatives. So far we discussed the local variable importance measures, and but let me mention some of the limitations of these local variable importance measures. So, for example, if we have two covariates xi and xj, which are highly correlated, then gamma I will typically be close to 0, potentially underestimating the importance of xi. Furthermore, LOCO does not capture interaction effects well. So a variable might appear unimportant alone, but be crucial in interaction with another feature. And also, as we have seen, the definition of loco relies on an arbitrary choice of the subset of S, and potentially we may wish to work with importance measures, variable importance measures that avoid this kind of arbitrary choices. So another example of variable importance measure that we studied in this project was Shapley value. So let me motivate a little bit where the Shapley value comes from. So originally this idea comes from cooperative games theory, which aims to distribute the payout among a group of cooperative players in a fair manner. So for example, imagine a situation where a group of players A, B, and C play together a cooperative game, and as a result, they obtain a total payout of $19. And now we would like to understand how to distribute this total payout among these three players in a way that acknowledges their individual contributions in a fair manner. So Lloyd Shapley postulated that a fair payout allocation should satisfy the following set of axioms. Efficiency. So here the use of the term efficiency is different than the one that we are used to in statistics. So here it means sum of individual contributions sum up to the total payout. Then symmetry, meaning that the contributions of two players should be the same if they contribute equally to all possible coalitions. Furthermore, dummy, meaning that a player who does not contribute to any coalition should receive zero contribution. And finally, linearity, meaning that if there are multiple games, then the total contribution of a player is the sum of contributions from different games. So Shapley value is a unique credit allocation procedure satisfying above axioms. So this expression 8 provides Shapley value for a player I, where omega is a payout function. That is, it takes as input a subset of players, and as an output gives a payout that this group of players would obtain. So let's try to understand this expression a little bit better. And for that, the crucial part is the one marked red. So the difference of payout for subset of players S and player I minus the payout of subset of players S alone. So this difference tells us like what's the marginal added value in terms of the payout of adding player I to subset of players S. And then in order to compute Shapley value for player I, we compute the weighted average of these differences across different choices of subsets of S. So maybe let me illustrate it quickly on an example. So let's look at the picture on the bottom of the slide. So here again, we are looking at the game of consisting of three players, A, B, and C. And let's assume that we would like to compute Shapley value of a player A. So for that, we would need to look at the difference of payout of player A playing alone minus payout of empty coalition. Then the difference of payout of players A and B playing together minus player B, minus payout of player B playing alone. Similarly, payout of players A and C playing together minus payout of player C playing alone. And finally, payout of players A, B, and C playing together minus payout of players B and C playing without player A. And now averaging all these differences in payouts, we get the Shapley value for player A. So later, this idea of Shapley values has been adopted in the machine learning literature to assess feature importance in prediction models. And here we consider it we adapt it in the context of heterogeneous treatment effects. So Shapley value of I feature for Kate is given by expression 9, which is almost the same expression as the one that we looked at the previous slide, except of that now instead of having a payout function, we look at the difference of Kate functions. Also, what you can recognize that this red part of the expression 9 corresponds to local variable importance measure for a subset S of variables. So another way of viewing Shapley value is as a weighted average of local variable importance measures for different choices of subset S of variables. So just briefly going back to the example and picture on the bottom of the slide. So now we can think about A, B, and C as three variables. And if we are interested in importance of variable XA in context of heterogeneous treatment effects, then again, we would look at the difference of Kate conditional on XA minus just average treatment effect, then difference between Kate conditional on variables A and B minus Kate conditional on B alone, then difference of Kate conditional on A and C minus Kate conditional on C alone, and finally Kate conditional on A, B, and C minus Kate conditional on B and C alone, and calculating the average of all these differences, we obtain the Shapley value for variable XA. Okay, so let me now present some simulation results. So the results that I'm presenting here are for three types of variable importance measures that are previously introduced. So two types are of local variable importance measures. So leave one out and keep one in. So these correspond to first two rows. And the bottom in the bottom row, we can see results for Shapley values. So in the first column, we see the results under the null setting, whereas in second and third column, we see the results under smooth and rough alternatives. So the results that I'm presenting here are results of testing zero importance of variable x1 in our simulation setup. So we're testing importance of a single variable x1. And different simulation scenarios are indexed by two parameters, beta and sigma. So parameter beta quantifies the importance of covariate x1. So in particular, cases of beta equal to 0 corresponds to null setups, and beta larger than 0 to either smooth or rough alternatives. And sigma is a pairwise correlation between different covariates. So I guess two main takeaways from these simulations is that our procedure controls type 1 error under the null. However, it's a little bit conservative, which we can see in the first column. And also the power goes to 1 as the sample size grows. Okay, so let me also talk about the application. So the data that we studied came from a global phase 3 randomized placebo-controlled efficacy trial of Sanofi's bivalent SARS-CoV-2 recombinant protein vaccine with GSK's AS03 adjuvant. And this trial has been conducted among adults aged 18 and older. So here, vaccinations or placebo were administered on day 1 and day 22. And the study was conducted in 2 stages. Stage 1 assessed a monovalent vaccine containing the original SARS-CoV-2 spike protein. And stage 2 evaluated a bivalent formulation, including both this D614 and the beta spike protein. And stage 2 of the trial enrolled over 13,000 participants between October 21 and February 22. So our analysis focused on per protocol stage 2 cohort that had evidence of previous SARS-CoV-2 infection at enrollment. So the data set included 597 individuals from Ghana, Honduras, India, Japan, Mexico, and the US. So the treatment, so the patients were had the randomized assignment either to vaccines. These were 305 individuals in our data set, or to placebo. These were 292 individuals. Furthermore, we considered the following baseline covariates. So among demographic factors, we had age, sex, BMI, and country. And we also had information on 2 immunological markers. That was baseline neutralizing antibody titer against the BA1 strain and concentration of binding antibodies against the Omicron strain. And the objective of our analysis was to answer the question how baseline characteristics influence the effect of COVID-19 vaccination on an immunological outcome, which in this case was neutralizing antibody titer against the BA1 strain of SARS-CoV-2 measured at day 43. So let me present some results of the analysis. So here you can see point estimates and confidence intervals of different variable importance measures for different baseline covariates. So here I'm presenting results for again, these 3 variable importance measures that I previously introduced. So keep one in, leave one out, variable importance measures, and Shapley value. So I guess the main takeaway from this picture would be that for 2 of the baseline covariates that we considered, so for one of the biomarkers that is neutralizing antibody against BA1, and for variable country, two of the considered variable importance measures, that is KIP1N and Shapley value, suggest non-zero variable importance. Okay, so let me summarize. So we present an inferential framework for evaluating variable importance for heterogeneous treatment effects. We provide efficient estimator of this measure together with corresponding confidence band. So I didn't talk about this part in this talk. And we introduce a wall type test to assess the null hypothesis of zero importance. And our approach focuses on local variable importance measures that vary among individuals, coupled with global inference that assess the overall significance of a variable across all individuals. So here are some selected references. And thank you very much for your attention. And I would like to acknowledge the support of Pacific Institute for the Mathematical Sciences and eScience Institute at UW. And I'm curious to hear your questions and the discussion.
Yeah, well, thank you. Any questions? Any brave volunteers? Oh yeah. I don't know
Okay.
if Ali was saying
Oh,
hi or he had a question.
I have a question, but sort of, Andrea, if you want to go first, please go ahead.
No, you go first. You go first.
Paul, thank you for sort of a great talk. Um, so first a clarification, because you talked about, when you talked about local, you mentioned that sort of some of the limitations of local. But am I correct to understand that sort of Shapley has the same limitation when it comes to correlated variables and interaction?
Yeah, so it has some of this limitations. So one of the tables that we are including in like in the paper is the following table. So I guess something I realized across along working on this project is that when talking about variable importance measures, I guess one need to be like very clear in terms of definitions, and like different variable importance measures, they seem to be capturing a little bit different aspect of variable importance. So in particular, in this table that we included in the paper, we were trying to think about different cases where one of these variables would be close to one, but the other not necessarily. And that would kind of suggest that they capture a little bit like different aspects of variable importance. And pretty much we were able to find each combination, right? That you can always come up with some kind of a setup where one of these variables would be close to zero, whereas like the others would not. And yeah, in particular, like in the case where variable is highly correlated with another variable, then especially like leave one out would be suffering from that. Or if variable is highly correlated with many other variables, then both leave one out. And yeah, then Shapley value we would also expect to
makes sense. So
have
leave one out is more sensitive to sort of two variables being correlated, but Shapley, if a variable is correlated with others, it would be potentially more susceptible to that. I mean,
yeah, exactly.
And so I don't want to get into philosophical issues on sort of what it means for sort of importance of a variable with Shapley in particular. because to me, it's difficult to interpret from a statistical perspective. And so I don't think that that's the point of your talk. I mean, you're providing a sort of a general framework that sort of also applies to Shapley. But I don't know if you have any thoughts on that. And
yeah, I mean, so I agree that it's more challenging to interpret, and like as you're mentioning, like I view these examples that I presented as, let's say, special cases from like a more general framework that we are presenting in the paper. So I guess like keep one in variable has fairly simple interpretation, meaning, let's say, like what's the single most important variable that when I'm including it in the model, leave one out, then that's okay. If I have like a full vector of variables, like what's the single variable that like I'm able to remove, I don't want to remove. In case of intuition behind Shapley value, I think the easiest for me to think about it is in terms of its definition. So there is a definition of Shapley values in terms of permutation of variables, that you look at all permutations of your vector of covariates, and you kind of follow each permutation up to the point where you get to your feature I, of which you're interested. And then you're looking at the difference, okay, all the variables that I've seen so far, including I and without I, and you look at all these differences across all the permutations. But yeah, whether, that will be intuitive for a clinician, that's like another question, right? So I agree that there is definitely a challenge there to communicate it and have a clear intuition. I think you're muted now.
so I was just going to say that unfortunately, Mark was not here to ask you sort of what I want to ask you next, but sort of, I mean, he would have been in a better position to ask. But sort of maybe Andrea is going to ask that question sort of, or something related to that. So I'll shut up for now, wait for her to ask something, and I'll come back.
I'm rubbing my head. Well, first of all, great talk, Pawel. I enjoyed your talk. I have a couple of questions. The first one is I'm not sure the overall what's the goal of this exercise. I mean, at the end of the day, what these X's are is effect modifiers, right? I mean, effect modifiers in the additive scale. And what I'm looking at is the excess effect modification of one variable. I'm thinking of leave one out. After I'm accounting for all the other covariates, why do I want that? I mean, from a scientific perspective, what do I gain from, to me, nearly everything is an effect modifier. There's very, very few things that are not. And what do I gain from that? I mean, I understand Kate is important, but I'm not sure I understand why I want to search for this variable importance. I'm not sure about that. But let me ask you the second question. This one is more, it's perhaps easier. I mean, the first one was more like philosophical. I just don't grasp why this exercise is something I want to engage in. But the other one is, this whole thing relies very much on the scale of measurement. Like if you have a measurement of if y you do a transformation that is nonlinear, all of a sudden the variables that pass the test of being important may not pass the test, or is it not that case? Is that the case or not? I mean, like if I take the logarithm of the variable and I do now, Kate, but on the logarithm of the outcome rather than the outcome itself. which, someone might be choosing to measure things in the log scale. Then, do I keep the same variables? Is this scale invariant? Is this exercise scale invariant? Any of the approaches that you chose. I think it's not, but I may be wrong. You see?
Yeah, I think you may be right that that may be not scale invariant.
I mean, linear transformations are fine, but I don't know that it's going to be scale invariant. Anyways, I don't know, Ali, if those were your questions at all.
No, I wanted to ask sort of a simpler question. You have deep questions. I wanted to ask sort of if there are connections with, in particular, the work that Marco and Peter and others have done, because they also come up with like a general measure of variable importance. Theirs is sort of in a predictive setting, but sort of I would imagine that sort of it would
Makes
transport,
sense.
directly to this setting as well.
Yeah. So there is some connection. So building up on Marco and others' work on variable importance measures, there was also follow-up work by Oliver Heinz and Stijn van Stellen that they adapted kind of that approach to heterogeneous treatment effect. So I would say one major difference is that the measures that are considered there are global variable importance measures, whereas the ones that we are defining here are local variable importance measures. However, if you would be interested only in this problem of hypothesis testing that I was presenting here, then at the end of the day, the test that I was presenting here was also global, right? So
yeah, that's what's...
So if we are interested only in testing, then let's say that leads to the same testing problem, which is global. However, in terms of the definition and like also in paper, we discuss like confidence bands and so on. And then the variable importance measures itself, like they are defined as local objects.
I see. Thank you. Thanks for clarifying that.
Yeah, so maybe like coming back to your questions, Andrea, like especially like the first one where you were saying that pretty much everything is or can be affect modifier, but like for example, looking at this plot, like I guess I would view only like these two variables that I would be able to say, at least based on these results, that they are potentially effect modifiers.
Yeah, the reason I connected to the other question about the logarithm is because effect modification is so much dependent on the scale. I mean, what you are measuring, whether you are measuring the on the additive scale or the multiplicative scale. So I'm having a hard time grasping the whole goal, because on any scale that I give you, I may find a completely different set of variables. I don't see the same issue when it's prediction. You see, for prediction, I understand the importance of variable importance. I mean, you want to get at the right set of variables so that, you can predict accurately an outcome. But here is treatment effect. So it depends how you measure the treatment effect, whether, it's an additive scale and, a multiplicative scale and so forth. So anyways, I mean, it's more philosophical. There's nothing against the technicalities. I do have also a hard time grasping the Sharpley, measures, but I guess because I'm ignorant on on the topic, on game theory. So anyways, I don't have that intuition. So
But like if I understand correctly, like in terms of prediction models, like one way of thinking about this like variable importance measures would be also that you build two models, let's say, like one's maybe including all covariates, one's removing one, taking the difference. So why this scale invariance is problematic here and not that?
It's not that it's problematic. It's that
Mhm.
I can see that if I am trying to predict, I'm thinking of machine learning, I'm trying to predict an outcome, it's important to know which variables I want to go and collect for predicting the outcome. That will help me. But if I'm doing treatment effect, why do I want to discard some covariates? I mean, why do I want to, I'm going to, this is for the doctors when they are going to say, well, if you take this treatment, you are such and such person with such and such covariate. If you take the treatment, you're going to benefit by so much. I don't know. I mean, anyways, I don't know so much about, why do I want to discard some of those variables? I'm not sure I see the. Anyways, I don't want to.
But like for example, like in case of like Kate estimation, like often these procedures are kind of like two-step procedures, and in first step you have, let's say, your covariates that are sufficient for confounding adjustment, and there of course like you want to have everything that is needed. But then like when you define the Kate function, it can be like conditional on subset of variables, and I guess I would argue that you not necessarily want to condition on everything that you have at hand, right? Like you want to condition on subset of, let's say, few meaningful variables. So at least my understanding or hope would be that maybe this kind of approaches could help you to kind of identify this set of variables that you're conditioning on.
Okay, I'll think about that. Thank you.
I would love to understand, Andre, your question about and your connection that you're drawing here with effect modification. Are you saying that the null hypothesis is too strong? Sorry, I know maybe there's two different issues here. One is the interpretability and objective that's being considered. But when you bring up effect modification specifically, is that about the null hypothesis as being not a null that you're interested in?
Not which null hypothesis? The null hypothesis of leaving one out doesn't change the result.
I'm just trying to understand where effect modification comes into this.
Well, because I'm saying that the ATE changes with X. Let's take 1X versus nothing, okay? And I do not believe that ATE. I do not believe that the difference between the outcome, the counterfactual outcome, if you're treated and if you're not treated, is homogeneous. I mean, there's so many reasons why that difference varies across individuals, and I cannot imagine any one single X being discarded. Most biological, causes are going to impact.
But I guess also some more than the others, right? And some of them you may not have, let's say, enough data or enough information to.
Well, but that's not a reason to discard it, right? I mean, that's just a reason for saying, the test will not be able to detect that variable is important. But it's not necessarily a reason for discarding the variable.
But like let's say we have Kate function, right? And we have, let's say, 100 covariates at hand. Like we could compute like Kate conditional on all these like 100 variables. But maybe for a clinician it will not be so informative, meaningful. even though one
Mm-hmm.
could argue that for each of these variables, there is some kind of like variability, heterogeneity, and so on.
Mm-hmm.
Like, I
Mm-hmm.
guess ideally we would like to identify maybe two, three that where there is like highest heterogeneity and where also clinicians can somehow meaningfully interpret it and so on.
Yeah, yeah, maybe, yeah. I want to think a little bit more about it, but yeah, maybe. Anyway,
I also see Aaron is raising.
Yeah, yeah.
Yeah.
Thank you.
yeah.
Nice talk. I guess I'm wondering on the same topic, if you've given any thought to there being relationship between your work and identifying optimal treatment rules. Because I guess I could imagine, like you're sort of saying, settings in which if you want to identify an optimal treatment rule, that's going to depend on the conditional treatment effect, and maybe you want an optimal treatment rule, or at least a treatment assignment rule that's going to be more explainable instead of being really black boxy, and maybe being able to identify variables that are really important for treatment assignment is something that your procedure could help with. Have you thought about that at all?
Yeah, so I must say I was not thinking much about dynamic treatment regimes in this context, and like it's not immediate to me to see how it could be used, but yeah, it sounds definitely very interesting.
Thanks. And then a second, more technical question was I'm wondering how you're getting the confidence intervals on this slide, because it looks like the limiting distribution for your variable importance measure is going to change based on whether the null holds or whether the alternative holds. So it would be like the RKHS norm of a Gaussian random variable under the null, and then something probably normally distributed under the alternative. Maybe you mentioned this and I just missed it. But I guess I'm wondering how you're dealing with the distribution changing depending on the value of the unknown parameter.
Yeah, so yeah, like in the paper when we present the kind of form of it, like we have to deal with it a little bit separately, like as two separate cases.
Thank you.
We had two other questions in chat. Nolan was asking on a slightly different, type of question, a bit more technical of a one. What kind of
Mm-hmm.
kernels? I think you may have mentioned it, but I also was curious. So, what kind of kernels were you using when you projected into the RKHS?
Yeah, so for the embedding, we were working with Gaussian kernel. So at some point, I was mentioning that we want that the RKHS embedding is an injective map, and for that you need a kernel that is universal. And I think like some of the common choices of the kernels, like Gaussian or Laplace kernel, they are universal. So I would say that that's something I would be aiming for. And I guess another related thing is kind of choice of bandwidth. So for this work, we mostly relied on median heuristic. But yeah, that would be also something worth investigating a little bit more how it kind of behaves for different choices.
And then Albert had a follow-up question on Andrea. So, just reading verbatim, so I don't need to process this at the same time as I read it. Can I think of these procedures as a way to identify variables that might explain heterogeneity?
Yeah. So I think this is how I would try to think about it. That like you want to identify variables that, let's say, capture the most of it.
And then if no one else has any questions in the meantime, maybe I can ask a more speculative question of my own. So that table you showed, I'm incredibly fascinated by. Um, so what is your takeaway after you've done this simulation? Like, maybe not for this work, but for future work, now that you've observed that this is kind of all laced
Mhm.
into the discussion we've had. So now that you've observed that depending on what I define as variable importance, I may or may not conclude completely wild things from my peers.
Mhm.
What is your philosophical takeaway from this? Because this seems a little alarming to me, but maybe this is also opportunistic about future things to think about. So I'm just curious about your perspective.
Um, I mean, probably I will not surprise you, but I guess like one of the takeaways that I had, let's say, from looking at this table or coming up with this table is that there doesn't seem to be like a golden bullet variable importance measure, and that I guess potentially suggestion would be to compute several of these, and actually I find the cases where they don't align as potentially most interesting cases, because then you can try to study, okay, given this variable importance measure, what I know that it kind of captures, and what are some other uh, aspects captured by the other measures. And I think like these discrepancies tells you something kind of like which aspect of variable importance you're observing. And I guess maybe the second point is like also like in the meantime, reading some other papers on variable importance measure, like I started noticing like how often people are vague about the notion. They just kind of talk about like general variable importance, but like if you don't specify the estimate or the quantity, like it's even difficult to start trying to understand what's kind of happening. So yeah, I guess it's potentially especially important to be, I know, clear at definitions.
Ali, I'm going to jump in ahead of you here because my question relates directly to what was just said. I was wondering, Pawel, with the figure that you showed, you were comparing your three different variable importance measures. But as you said, are they actually estimating the same quantities? Are they really comparable with respect to scale?
So you asked my question. Thank you.
I mean, so like if the question is whether like the estimand is exactly the same, like no, it's not.
Okay, so a 0.03
so
and a 0.01 for two different variable importance measures have nothing. It cannot be compared.
I mean, so I think that the way I was like viewing them was like more in terms of kind of how each of these variable importance measures is defined and what is it capturing. But yeah, like at the end of the day, like the estimand is a little bit different, right? Like for leave one out, it's kind of Kate conditional on everything minus Kate conditional on everything except of single variable. In the other, for keep one in, it's Kate conditional on single variable minus ATE. So like these are, at the end of the day, these are different quantities, different estimates. So yeah, in this sense, one could say, yeah, they are not kind of immediately comparable, but I would say like they are like still informative through capturing like different aspects of importance. Yeah.
So you say they each
Makes
have
sense.
value for their own respective objective, even if they shouldn't be directly compared within each other.
I mean, so yeah, like the way that I'm interpreting them is that yeah, they capture a little bit like different aspect of variable importance. So for example, like in this let's say language of effect modifiers, like when we talk about like keep one in, then I would view it as that keep one in variable importance measure provide us some kind of information about like unconditional effect modification of a given variable, whereas leave one out provides us information about effect modification of a given variable conditional on all the remaining variables. So that's a bit different information that we're getting. like both of them, they quantify some aspect of variable importance, but these are a bit two different pieces of information.
All right. Given that it is past 1 a.m. for Pavel, let's let him go. But certainly email Pavel if you have more questions, because from this wonderful discussion, it seems like there's a lot of new opportunities and further research to be done, which we would love to be engaged with as a department and certainly with Pavel. So with all that being said, thank you so much for attending. Very much thank you to Pavel. And I will see you all next week for the next seminar.
Yeah,
Thank you very
especially
much
thank you for
for
staying up late.
thank you very much for having me. It was great to see you all, and thank you for all the great questions and discussion.
Thank you, Pavel. Thank you, Pavel.
Thank
Of
you.
course.
Pavel.
Bye-bye.